Hello, good evening, bonsoir, Annie. Welcome to this virtual Science North Star Party. I'm Olathe, staff scientist for Spaceplace and the Planetarium, and this is Lucy. She is the science communicator for the Planetarium, and she will be giving us a night sky tour this evening. We are also joined by a special guest who is a fellow science communicator who studied astrophysics and some very special black holes. Jesse Rogerson. Hi, Jesse.
Hello.
So Jesse will be talking to us this evening about black holes and astrophysics in Canada. And we are streaming to you from Sudbury, Ontario, in Swakamak. We are on the traditional and ancestral lands of the Atikameksheng, Anishinaabeg, and Wanapitei First Nation. This land sits in the Robertson-Huron Treaty Area. For those of you joining us live, please let us know where you're joining us from, and also leave your comments and questions for us throughout. We will do our best to answer all of your questions and have some fun as well by joining our quiz. So we have dropped the link to the quiz. It's on Mentimeter. So that's in the comments. So get in there, get ready, and pay attention to Jesse's presentation because that will help you answer the quiz. And if you win, you have the excellent prize of bragging rights. All right, over to you, Jesse.
Hello, there we go. Over to me. Okay, let me share my screen. It's so good to be here. Oh, before I share my screen, I'll just say that I want to reiterate the note that Olathe just mentioned related to acknowledging the land that we're on. And I think that wherever we all are, we should all think about that once in a while. And it's good to remind ourselves of it and remind ourselves that there's work to be done just on our own personally. You can read, you can meet people, you can talk to people. It's really great things to be doing. So I encourage you to all look into that. So I'm going to jump into my presentation. So let me just share my screen here. There we go. And here we go. I study black holes. I am Jesse. I work at York University. And one thing, just a quick note I wanted to mention. So York University, it's in Toronto, and it's got this really great astrophysics department with some incredible researchers and grad students and undergrads. And on campus at York University, there is this observatory called the Alan I. Carswell Astronomical Observatory. It's run by Dr. Elena Hyde. And the group there, does incredible things. They do really great stuff. And I just have some cool pictures of it. And the reason I'm putting these pictures up is because I want to really punch the homegrown Canada stuff here, because Canada is one of the best countries in the world when it comes to astrophysics. We really punch above our weight. What I mean by that is if you look around the world and look at all the countries that research, that have universities and professors and grad students and undergrads that are learning astrophysics and researching astrophysics, they are publishing as much or more than just most countries around the world. So we are really one of the best in the world at astrophysics, and it shows. I mean, we are part of some of the biggest projects in observatories around the world, like one we'll talk about later. And right here at York University, we have this incredible 1-meter telescope on campus, which you're just seeing here, brand new telescope just installed. So I just wanted to give a sort of a big ups to Canada there, because we do a really good job in astrophysics.
And they do online programming as well. That's the first online event Jesse and I did together was
That's right.
Jeopardy.
Yes.
Really and I have the
Did you win that? It was you, right?
Yeah.
Yeah. That's right. The observatory. See, this is what I mean. Like, if you look around Canada, there are so many great people talking about space, learning about space. We're really, it's sort of a big part of our country. I mean, just look at our $5 bill, or is it $10 bill? One of our bills had the Canadarm on it, right?
Yeah.
Yeah.
It has Canadarm, an astronaut, and Dexter.
Dexter, of course.
Yeah, we're really well known for space robotics and astrophysics as well. So
was that Hadfield that was on? Was it actually him on the?
It's like in a spacesuit.
Yeah, who knows, right? Could be anybody. So I study black holes as sort of the work I did a little bit more formally. I still do a little bit of it now. I'm primarily an educator now, but I still do a little bit of research on black holes. So let's dive into that. and then we have tons of time for questions and other things related to black holes a little bit later. So the number one question here is that I always get is, what exactly is a black hole? And we all kind of have a sense of it. We all kind of think about this. We're like, oh yeah, it's that like vacuum cleaner in space, or it's that thing that sucks everything up or whatever. It's a big hole in space or whatever. Well, that's sort of kind of true, but also not really 100% true. So before we really, let's get an understanding of the physics that's going on here. And we're going to start with just a simple thought experiment. If you have a soccer ball and you go out of your house and you go out into a field somewhere and you take that soccer ball and you throw it as high as you possibly can. Let's think about this experiment in our head. If you throw it as high as you possibly can, what's going to happen to that soccer ball? It's going to climb into the air. It's going to accelerate off your hands. And then as soon as it leaves your hands, it's going to start slowing down because there's a gravitational pull on it and it's being pulled back down to Earth. And it'll reach a point where it gets to its highest point, and then it'll come back down to you, and hopefully you'll catch it, and it won't hit you in the head, of course. So this is a very, I'm not trying to be crazy here. It's a very simple thought experiment. You all understand how gravity works. You throw something up into the air, and it comes back down. You can give it a little bit more thrust, and it'll go a little bit higher. You can give it a lot of thrust, and it'll go even higher. But gravity is always working to pull that object back towards, say, Earth, if that's where you're starting from. So that's a simple thought experiment. Now let's do the exact same thought experiment, but let's think about it with a flashlight. Exact same thing. You walk out into a field, you have a flashlight in your hand, and you point your flashlight up and you turn the light on and it shoots the light up. What happens to that light? It's working in a gravitational field just the same as the soccer ball is. The soccer ball, as soon as it left your hand, it's being pulled back to Earth by the gravity. What's happening to the light, right? If you think about it, you're all probably coming to a similar kind of conclusion here, and that is that the light is going to leave the flashlight, and it's just going to keep going. That light is going to go up into our atmosphere. It's going to keep going. You're not going to see it come back and shine in your eyes, right? It's just going to go straight up. Even though it's working in a gravitational field, it's working in Earth's gravitational field, it just, off it goes, off it leaves. Well, the definition of a black hole is an object that has so much gravitational field that it even pulls the light down. So you imagine, if you could, you could stand on the surface of a black hole. So you can't do that because that's impossible. But just imagine you could. This is a thought experiment. We can break all the rules. You're standing on the surface of a black hole and you have a flashlight in your hand. You shine that flashlight up, that light goes up, but the gravity is so strong that it actually pulls the light down. So you would observe the light to go up, to stop, and to come back down, to bend back towards your eyes and return to you, just like the soccer ball does on Earth. And if an object in space can do that, then it would be defined as a black hole. So now you know what a black hole is, but there's a little bit more to it. And I'm going to give you just a sense of size and scale here. So here you have an image of the sun, and I have it's a really fantastic image of the sun, and we have the size of the sun right there. It's about 1.4 million kilometers wide, so it's very large. The Earth is very small in comparison. It would be just a little tiny dot on this image. And what I've done here is I've given you the mass of the sun in units of the sun. So the sun weighs as much as one sun, which makes sense, right? The sun weighs as much as one sun. It's one solar mass, right? So let's talk in terms of, think about black holes again. There's actually two kinds of black holes out there. The first kind of black hole is a stellar mass black hole, or a stellar black hole. Now, this gives you a sense of scale here. They're really small. Really, really small. They're only like 100-ish kilometers wide, roughly speaking. So little tiny things in comparison to the sun, but they weigh much, much more than the sun. For example, they can weigh 10 solar masses, 20 solar masses, or something like that. So it's 10 times the mass of the sun crushed into a space that is really, really small in comparison. And we call those stellar mass black holes. And there's millions of those within a galaxy like the Milky Way, and they come from when stars die. That's one kind of black hole. But the ones that I like, the ones that I study, are supermassive black holes. And that is the actual term for them. It's not just a cool Muse song. It's supermassive black holes is the scientific term for a black hole that has as much as 1 million or 1 billion solar masses. So this is millions of times the mass of the sun all crushed into a space. But as you can see, the space in this case is a lot larger. It's a lot of mass in a very large area. It's something like 10 million kilometers wide or something like that. Very, very large. Now, if you could stand on the surface of that circle right there, or on the surface of this circle right here, even though they're not really a surface, and you had your flashlight and you shone your flashlight away, the light would bend and then come back, and you'd have a black hole, and that's what it is.
So when you say it's not really a surface.
Oh, Olathe, that's a good question. Okay. It's not really a surface. Now, here's the interesting thing about black holes is that all of that matter, technically speaking, black holes are infinitesimally small. They are singular points. If you imagine like a graph, if you go back to school and you make a graph with an x-axis and a y-axis and you put like a dot at like coordinates 3, 4 or something like that, that's a single point. It has no shape, right? It's a single point on a graph.
Yeah, we hear that, the singularity.
The singularity, right? Singularity. That's what a black hole is. It has no shape. It's all of that mass mathematically squished into an infinitesimally small place.
But we still talk about kilometers wide.
Yes. What do I mean by that? That's the distance at which you have light has to be away from it in order to escape. So anywhere within that region, anywhere within this region, light cannot escape.
Okay, I see. Yeah. That's like one of those things that had been like messing with my head because I'm like, I know there's singularity, but I know they have diameter. So like, okay, thank you.
So here's the interesting thing is that if you're like, say you're a spaceship or something and you're flying and you pass by that boundary, like it's not related to the black hole in any way. Like you're not like, you wouldn't notice anything. You just fly past that boundary and you would still be you, and the black hole would be in the distance, somewhere in the distance, and you'd be flying towards it, but you wouldn't know that you passed it necessarily because everything would be relatively normal.
But that would be a point you couldn't go back from either.
Exactly. Light, most importantly, light couldn't go back from there.
Yeah. Okay, let's go.
All right, now we know. Now, more specifically, I study quasars. So quasars are the coolest things in the universe. And that's probably, that's a weird way of saying they're like one of the hottest things in the universe, but they're super cool to talk about. Now here, this is an artist's impression of a quasar. That's what you're looking at here. And a quasar is two things. It's a supermassive black hole that is in the middle of eating up a whole bunch of stuff. And this image displays it very, very well. If you look way down towards the center of this image right there, there's like it's hard to tell, but there's like a little dark circle right there. That right there is the supermassive black hole in this image, in this artist's impression. And so that would be something like 10 million kilometers, that region where light can't escape from. And all of this material you're looking at is gas and dust and like torn up stars and torn up planets and stuff, all circling the drain. Just like, imagine you had a sink full of water and you pulled the plug and the water starts circling, all trying to get down the drain, but not all of it can get down the drain at once. That's exactly what's happening here. We call these accretion disks. And
sorry, we just have a question from the comments. So someone is asking if that beam of light is a relativistic jet.
Yes, that person clearly knows their black holes. That is a relativistic jet, absolutely. We see these in 10 to 20% of supermassive black hole, of quasars. We see 10 to 20%. And this is related to a couple of things. As all that material is swirling down, this is a really energetic process. A lot of material trying to cram itself onto the black hole at once. There's a lot of energy. It's moving really quickly. So the stuff way down towards the edge of the black hole boundary is moving at like super fast speeds. And there's a lot of magnetic fields tied up into it. And as a result of this energy and momentum and magnetic fields, you get these massive jets that funnel energy away from the supermassive black hole and the accretion disk. And they're really, really bright. It's a lot of energy that's really condensed into a beam. And they're very bright if you're looking down the beam. But if you're not looking down the beam, then you don't really know that they're there.
Because it's all going straight.
Exactly. It's kind of like a neutron star and pulsar relationship. All neutron stars are neutron stars. Some of them act like pulsars because we look down a beam of jet that they also have. This is just on a much, much larger, this is on a galactic scale, whereas a neutron star and pulsars are on a stellar scale.
Wait, does that mean like pulsars it's just because of our perspective on
Exactly. Yes.
Oh, okay. That's interesting. And so we know like nothing can escape a black hole, right? Like we always hear that to singularity and nothing can escape. So this relativistic jet of like extremely energetic particles that are kind of being, they're escaping from sort of the event horizon of the black hole. They're not actually being emitted by the black hole. They're being emitted by sort of the event horizon.
Yes, exactly. You're exactly right. Anything that goes beyond the event horizon, that goes beyond that boundary that light can't escape from, we'll never see again. The jet is originating from outside that and is all of this light as well, originating from outside the boundary, so we can see it. And we learn a lot about the black hole from studying the jet and from studying the accretion disk. And the accretion disk is what I actually study as a researcher. If you look in this artist's impression, you see these big wispy, what look like what we call winds. So there's massive wind generated by this because there's so much pressure from the radiation. All the light that's here is literally pushing gas away.
That's the kind of wind, when we say, like when we talk about solar weather and the solar wind, this is the same sort of wind. So
yes.
Black holes also have wind?
Yes. Supermassive black holes create so much wind that they can influence the entire galaxy that they live within. So the wind is a really important part of the quasar and the galaxy that it lives within, and studying it because the winds themselves are very random and they change quite frequently, and studying how they change lets us know about how much material is there and what the material is made of, and how the black hole is influencing the galaxy. It's really, really interesting stuff.
That's neat. So that's, where you're learning from something, not by direct, kind of an indirect way of, we do that a lot, right?
Yes.
Things from indirect measures. We did have one more question.
Okay.
Just wondering about the material, if the material is significantly adding to the mass of the black hole. So like you said, the black hole is like eating planets and everything.
That's a great question. Significantly, no. They are certainly growing. Like they get more massive as they eat more stuff. But like we're talking, like these things are millions or billions of times the mass of the sun. If it eats like 5 stars, like it's not even going to know. It's like a drop in the bucket, right? Okay. But there is a lot of material there surrounding the black hole, but it's not all falling onto the black hole. It's almost orbiting. Like if I go back, like it kind of orbits. It all kind of crams up against itself, and it can't get onto the black hole because there's other stuff in the way. And so this disk will eventually be entirely eaten by the black hole over millions of years, but it won't significantly change from, like, it won't go to 10 billion or 100 billion solar masses. It's a drop in the bucket. The way you get a supermassive black hole to grow significantly is for 2 supermassive black holes to merge with each other. And that's where the growth really happens.
Okay.
Good question. Okay, that's sort of my research, but I wanted to just quickly, because I have to mention it because we have to, and it's coming up, is the James Webb Space Telescope. Finally, the James Webb Space Telescope has announced, the consortium has announced that it is ready to be launched. They have a launch date of December 18th, 2021. That's only a few months away, 4 months away or so. This is an artist's impression of the JWST telescope in space. It is being called the successor to the Hubble Space Telescope, though I'll talk about why that's a little bit misleading in a second. But one thing I really wanted to point out is that Canada has a stake in this telescope. We have a 5% stake in this telescope, meaning we get 5% of the observing time. And that is huge. When it comes to the Hubble Space Telescope, the previous sort of flagship telescope of NASA, Canada didn't have a firm amount of money into it. And so we weren't, in order to get time on the Hubble Space Telescope, you're working, in collaborations. Whereas in this case, Canadians are going to have open calls and open proposals to this telescope. Couple of things just to compare the two is the Hubble Space Telescope is 2.5 meters. The diameter of it is 2.5 meters, whereas James Webb Space Telescope is 6.5. JWST is 6.5, very large. The orbits are entirely different. The Hubble Space Telescope orbits Earth at 525 kilometers above the surface, whereas JWST is being launched into a solar orbit, technically a solar orbit. It's going around the sun. It's actually going to be technically orbiting the L2 point, which I'll talk about in a second, and it's going to be 1.5 million kilometers away from Earth. Most important with this, you can fly to the Hubble Space Telescope and fix it if it breaks, which they've done 4 or 5 times. Mm-hmm. You cannot fly to the JWST once it's in its resting spot. It's there. So if it breaks, you can't fix it, which is why that it's taken so long to get it right. They wanted to be sure that it's right. Now, I alluded earlier saying that JWST is being called the successor to Hubble, and it is in a sense, but it isn't really in another sense. And that other sense is what it observes. The Hubble Space Telescope is a UV and optical telescope, meaning mostly it's observing the light you can see with your eyes. Whereas the JWST is primarily an infrared telescope, which is the stuff that's a little bit, the wavelengths that are a little longer than what our eyes can see, beyond the red, literally infrared. So it's a different instrument built to see different types of things than the Hubble is being designed to build or designed to observe. There is another telescope that's currently attempting to get built. It's called Castor, and it's a Canadian telescope. And if it gets off the ground, Castor is sort of like a Hubble 2.0, where it's a UV optical telescope and it would be orbiting Earth. It'd be a really great thing. Okay. Oh yeah. Just to compare the sizes, there's the JWST primary mirror versus the Hubble primary mirror. So you can see the size difference there. Okay. L2 position, just in case you're wondering, there's the sun.
I know this word. I'm so excited. Lagrange. The L stands for Lagrange.
Lagrange point. For all those who love their mathematics and physics, there are a few of these Lagrange points, which are gravitational safe spots in two-body problems. I'm not going to get into the details, but the L1 point is really easy to understand. Here's the Earth, there's the sun. We can all understand that as you move towards the sun, there's going to be some place in between the Earth and the sun where gravity is equally pulling you towards the sun and the Earth. And that's the L1 Lagrange point. There is another interesting position at L2, and then there's a few others around the orbit as well. This is where we're flying JWST to, 1.5 million kilometers away from the Earth, and the Hubble is just sitting there orbiting around Earth, right there. Where are the black holes? Well, there are, like I alluded to earlier, there are millions of the stellar mass black holes, and in any given galaxy. For example, there is this one called Cygnus X1. It's 21 solar masses, and it's only 6,000 light years away towards the constellation of Cygnus. That's why it's called Cygnus X1. And fun fact, Cygnus X1 was the first confirmed black hole ever observed, and it was discovered by Tom Bolton, who was working out of the Toronto Observatory, the David Dunlop Observatory at the time in the 1970s. So go Canada. We discovered the first black hole out there. There is another black hole. This is a supermassive black hole called Sagittarius A star. And this is supermassive. It's 4.1 million solar masses, and it's at the center of our galaxy, which is towards the constellation of Sagittarius, 26,000 light years away. Every major galaxy like the Milky Way has one supermassive black hole. And for us, that's Sagittarius A star.
Very cool.
And finally, I have a cool video. I forgot about this. So this is our galaxy. That's where our sun is, right there. And right at the center is Sagittarius A star. And this is a video of real data showing stars orbiting the supermassive black hole at the center of our galaxy. So right there, wow. That's the supermassive black hole, Sagittarius A star. That's the location. And you can see all the stars orbiting it, whipping around it, like so. So this data was collected over a decade or two or so.
And it's actually those supermassive black holes that are creating sort of the well of gravity that our galaxy is sitting in.
Yes, partially. Yes, yeah. It's the
There's also the dark matter.
and in the collective gravity of all the stars towards the center as well. Yes. Yeah.
Okay.
Beyond our galaxy, you would find a supermassive black hole at the center of every major galaxy, like, for instance, M87. At the center of M87, that's the galaxy itself right there. It has a massive jet shooting out of it, as you can see right there. And this image was taken, this is the first actual image of a black hole, and it weighs it. So the black hole exists in this emptiness of light, and then this would be light bending around the black hole. Just like we expected. This is in another galaxy 53 million light years away. So there's just a couple there's 3 black holes that are out there in space that we could go look at, and I think we could do a little bit of tour and go check them out, right? I think that's what,
we could.
Lucy's
Lucy, can you show us where we would be looking in the night sky to actually be looking towards these black holes?
Yes, of course. Hello, everyone. So we're using here Stellarium Web. It's a free-to-use browser-based kind of like planetarium program that you can use at home. And we're going to start off with the first one that was mentioned, so the one in Cygnus. I'm just going to look at a star that's near it. So we're going to search for that companion star.
That's right. It's actually Cygnus X1 is in a binary system, so it's a black hole that's orbiting with another star. So it's a star and a black hole orbiting each other, and that's one of the ways. I mean, what the black hole is doing is it's actually sucking off material from the star and creating a little miniature accretion disk around the black hole, and that's what they found back in the 70s.
That is so neat. So yeah, so there is the star right in the constellation of Cygnus. So Cygnus is the constellation that's one of the constellations that's part of the Summer Triangle. So to help you guys try to find this, we're looking at the night sky, looking pretty much near close to above your head. So towards the southeast over here. And we have 3 bright stars that makes a very nice triangle in the sky. It's a triangle we get to see throughout the whole summer season. Hence, we call it the summer triangle. The triangle itself, we call that an asterism instead of a constellation. It's a simple formation of stars. And the summer triangle is in fact part of 3 constellations. So this star here, Deneb, is part of Cygnus the Swan. And we also have Altair and Vega. Altair is part of Aquila the Eagle, and Vega is part of Lyra, which is a music instrument. So Cygnus right here along its neck, we can find that binary star where we can find the, well, black holes. Can't, as we mentioned, we can't quite see black holes, but we can see the star that's near it.
And we can see the X-ray light coming from the accretion disk around the black hole. Yeah.
I don't know about you, but my eyes can't quite see that. But yes, that's why we have amazing tools to help us see more than just a visible light.
Yes.
Now, on to the next one, the Sagittarius. So this one's a fun one to try to find in the sky. Right over the southern horizon during the summertime, we get to find another asterism, a simple formation of stars that is known as the teapot because, well, it looks like a teapot in the sky. We've got the base, the spout, the lid, and the handle, and it's part of Sagittarius. It's one of the zodiac signs, half man, half horse, so it's a centaur with a bow and arrow. And the spout of the teapot, or the tip of the arrow of Sagittarius, it points towards that galactic center that we mentioned of our own galaxy. So we can see, since we are in our galaxy, we only see kind of like our galaxy from the side. So we see this haziness of light going above us if it's dark enough outside. If you're near a town or a city, you will not be able to see this. There's too much light pollution. So if you're in the middle of nowhere, you might be able to see this haziness of light. So we've got the Milky Way, which is the name of our galaxy, and off the tip of the spout of the teapot, or the tip of the arrow of Sagittarius, right over here underneath 3 Sagittarii around this area here would be the galactic center.
It's funny. I live about 45 minutes north of Toronto-ish, from downtown Toronto, and the urban and suburban sprawl still makes it so that I can't see the Milky Way, which is really unfortunate.
It is.
I didn't realize that it was right below that 3 Sagittarii there. So right, if you're looking there, if you are looking right down that spot, right below 3 Sagittarii, that means you're looking right towards the center of the Milky Way. The Milky Way is a big pancake, that like a pancake made of stars. It's flat and it's round and it's a whole bunch of stars. So when you look through it towards the center, you're looking through a whole bunch of stars, which is that cloud of light that you see, that we call the Milky Way. And we live towards the outskirts, sort of about a halfway to 2/3 from the center. And Sagittarius A star, which is the supermassive black hole, is right at the center, roughly. So that's where it is. There you go.
That is so neat.
Very cool.
So yes, it's kind of like over here. I was looking at pictures earlier, since Stellarium Web, you can't just search for Sagittarius A star, so I had to kind of use maps and try to find it myself.
That right there is a lot of fun. Star hopping is one of the funnest things to do. It's like a little puzzle where you have a map of all of the star field and the thing you're trying to get to, and then you need to like look at your map and then look at like the stars and like try and find your way around. It's the best.
Mm-hmm.
I will say, so I study quasars. Quasars are supermassive black holes that are actively eating material. Our supermassive black hole is not actively eating anything.
Oh.
It is what we call a quiescent black hole. It's a quiet black hole. It's a non-active black hole. It still sort of like nibbles here and there. It sort of snacks a little bit once in a while. But a quasar is like, it's just shoveling material into the black hole. That's what quasar
is. That just because the material around it is kind of far enough away, like it's finished?
Yes,
that's a really everything it can.
Exactly. Quasars only exist in galaxies that are really far away. And if they're really far away, then that also means that we're looking really far into the past. What we think, one of the going ideas of the relationship of a quasar, a black hole, in the galaxy is that a quasar is an evolutionary step for a galaxy, where the black hole at the center is in the middle of eating everything that's nearby, and then it slowly consumes everything, and then it's all done. And then with our galaxy, we see our galaxy in present time, and so it's already done a lot of eating. And so there's nothing nearby for it to be consuming. It's done all of that. So if a star gets too close, it'll get torn apart. But other than that, it's mostly quiet.
Very cool. All right. Is there? What's
yes. So there's that last one that I mentioned. But before we move on, I just want to mention that this time of year, right now, if we look outside, as long as there's no clouds out, you'll be able to see a nice little crescent moon. So the next few days, we'll have a little crescent moon. But this year, we also get to see Saturn and Jupiter towards the south. Very neat things to see. If you have a pair of binoculars, you'll get to see a bit more, like Jupiter's 4 largest moons, so the Galilean moons. If you have a pair of binoculars, really gorgeous to see. And then if you have a telescope too, you'll be able to see the rings of Saturn. So here's Jupiter with Ganymede, Europa, Callisto, and Io. So we've got the 4 Galilean moons of Jupiter. Jupiter has way more moons, but those are the 4 biggest ones.
What's really fun to do, I remember doing this back in my undergrad days, is going out a couple of nights in a row and like watching the moons of Jupiter like sort of move around, the four major ones. That's so much fun.
Yeah, it changes from day to day because they orbit Jupiter pretty quickly. So they change from night to night. And then we also have Saturn and its gorgeous rings. So
I was out yesterday evening, and Venus was like pretty close to that crescent moon, and that was gorgeous.
I saw that too.
Of course, there's something special going on with Mercury right now too.
What?
Yes.
I don't know.
We'd have to like go back a bit. Here we are. Mercury. So Mercury is at its greatest eastern elongation. So from our perspective, it's the furthest east from our perspective. So we will be able to see Mercury just before the sun sets.
Yeah, it's hard for us here in the northern. Yeah, in the northern hemisphere. But yeah, it's like right. I think the 14th is its absolute longest. So
Yeah.
the week leading up and the week after, if you're going to see Mercury, they're good times to see it because, as you can see, again, light pollution, right? The sun kind of washes Mercury out. So when it's a bit further away, it's easier to see. Very cool. Thank you, Lucy. Well, I think we better get into our quiz. We're like, maybe, hopefully we'll get some time in the night sky again after the quiz. But let's see.
There's a bunch of good questions too.
Oh, and there's a bunch of good questions.
But I guess we also need to get the quiz. Yeah.
Well,
right.
we can. The thing is, we can do the. Oh, I'm sorry. There. I don't like to start it because of this music until it's ready, but it's ready now. You can put it up. Thank you. And yeah, while we're doing these questions, we are also going to answer some questions from the audience while we're waiting for players to join. So one of our questions was pretty awesome. But first I want to say hi to Norm McGraw. Thank you for joining. Norm was my Anishinaabe instructor, and we ended up having lots of star conversations. And also we have Clicked Denif wanted to know how black holes are created.
That is a great question, and it is depending on the type of black hole, right? A stellar mass black hole, the ones that weigh 10 or 20 times the mass of the sun, those are created through supernova. So a star much larger than our star gets to the end of its life, and it crushes down on itself, and it reaches a point where it can no longer crush down on itself, and it rebounds, and that rebound sort of forces material beyond the brink, so to speak, and it collapses so much on itself that it does this runaway collapse, and you get a black hole out of it. And they end up weighing something like 10-ish solar masses. So big, huge star reaches the end of its life, collapses on itself, and makes a black hole. That's stellar mass black holes. Supermassive black holes, well, we're still working on that, because supermassive black holes, there's only one per galaxy, and they're not tied to stellar evolution. It's not about stars being born and dying. These are related to galaxies being born. So we're talking the supermassive black holes were forming in the very beginning of the universe, when there was a lot of material around. Not all of it necessarily was in stars yet. There's a lot of stuff nearby and crunching down. There's probably proto-galaxies smashing into each other, growing into bigger galaxies like the Milky Way. And all of that activity at the beginning forced material into, basically was a runaway collapse without any kind of star associated with it. So very different origins. Supermassive black holes came from the beginning of the universe. Stellar mass black holes are formed sort of randomly as stars die.
So I've also heard of primordial black holes, which are really small, right? To be fully honest, I don't know much about primordial black holes, but these are really, really tiny things that were formed at the very beginning of the universe and would have had some sort of runaway growth effect of some kind. But I don't really know much about them. I can't really comment beyond that. Yeah, that's fine. Yeah. I'll give a shout out to Line Sarazin, who's joining us from Moncton, New Brunswick.
Yay, Moncton.
Yay, Moncton.
I love the East Coast.
And okay, yeah, Clicked Enough says cool. Thank you for answering. And we have a few people in the quiz now, so I think we can go ahead and start. Maybe a couple people join in. See if we have any other. Oh, we do have one other question.
Oh yes.
So Matt Graveline is asking, can black holes be seen as a fault in the universe's fabric, like a glitch in the code?
A glitch in the Matrix, right?
Yeah.
Matrix 4 trailer is out, by the way, everybody, just so you know. Okay, anyway.
I saw that.
I know.
So excited.
This is a common question, very good question. And so it's certainly not a fault in the sense, like nothing's wrong. But we talked about this idea of a singularity, right? Where it's a bunch of mass in a place that is a single point, which is kind of hard to wrap your head around. And if you look at the way we understand gravity, and we understand gravity through Einstein's general theory of relativity. And GR, general relativity, described space as a fabric, three-dimensional fabric. Like imagine you had a blanket that you can stretch in 2 dimensions. That's a fabric. Imagine you had a fabric that could be stretched in 3 dimensions, which is weird to like picture in your head, but that's what I'm asking you to picture. that fabric can be pulled and tugged depending on the mass that's in it. So you put mass in it and it bends, the fabric bends around it. Now, black holes can create such a curvature of the fabric, and they can bend space-time so much that light can't escape from it, and we can't see beyond that bend. So we don't really know what's going on in there. However, the mathematics of the theory of general relativity do allow for the bending of space-time to be so extreme that it can create pathways to other places in the universe. It can bend space on itself. It can literally fold the fabric over on itself. Now, we have no idea if that's actually possible. I'm just telling you that the theory of general relativity allows for the mathematics of that. Now, how are we ever going to prove if that's possible? Even if you could fly a space probe into a black hole, you're not going to be able to get any information out. So it's up to the theoretical mathematicians and physicists to help us understand what's going on in there. But in terms of it being like a glitch or a rip, it's not like that. But it's certainly space folded in a really incredibly extreme way, and that might lead to some really interesting outcomes.
All right. Okay. Well, we have 5 players. Let's go ahead.
5.
Okay. So here is the first question. How massive is a supermassive black hole? So is it at least 1,000,000 times the mass of the sun? Is it at least 100 times the mass of the sun? Or is it at least 10 times the mass of the sun? So here we're talking about a supermassive black hole.
Who was paying attention? You got to be paying attention.
Okay, and oh no, time's up. Oh, and it shows the results. And yes, awesome. You guys were totally listening. You got this. Okay, but that means that you're head to head. So let's see if someone can pull out in front. So our next question. Here we go. We're starting the countdown. You have 20 seconds to answer the question. When is the James Webb Telescope set to launch? Now, to put this in perspective, when I was going to school, when I was doing my master's at the International Space University, we went on a tour and we saw a big sculpture of the James Webb Telescope, and they're like, this is launching really soon, next couple of years, and that was back in 2005. So this has been a long time in the making, and we're super excited that it's December. And well done, December, yes.
I remember when I was in grad school was like 2010-ish to 2015-ish for me. And I remember thinking, oh yeah, it's definitely going to launch during my grad school. Like, of course it's going to. I've been here, like, no.
Yeah. Okay.
But it's set to launch.
Yes. Okay, question 3 of 5. Starting the countdown. So we know that the James Webb Telescope is using a different wavelength than Hubble. What wavelength is that? Optical, UV, or infrared? So we talked about optical is what you can see, what we can see with our eyes, right? UV is the shorter wavelengths, and infrared is longer wavelengths. Nice, okay.
There you
We
go.
got some people pulling out in the front now. So infrared, like what do we see in infrared? Why do we care about infrared?
Infrared, so the reason JWST is targeting this is for a variety of reasons, but one of the main reasons is it's looking for very specific things that are further away, and it wants to see towards the beginning of the universe. Now, there's this thing called redshift. As the universe expands, it stretches light out, and so if you want to see the same object but further away, then you need to look into the redder end of the spectrum. You need to go further beyond. So if you want to build on what you already know, say from the Hubble Space Telescope, and you want to see deeper, then you need to look into the infrared, because that's how you get further
and you
away.
have that bigger mirror, like much bigger mirror too, to collect more of that light. So
Yeah.
we can see further back in time.
Yep.
Yeah, very cool. Okay. All right. Next question. So 4 of 5. And here's the countdown. So how far is Earth from the sun? This was in a diagram.
It was?
And we know that the James Webb Telescope is going to be even further, right? It's another 1.5 million
That's right.
kilometers past Earth. Oh, nice.
Yes.
Good work, guys.
You all
Okay,
know.
and now we're on to our last question.
I'm excited to see who the winner is.
So what is the name of the supermassive black hole at the center of our galaxy? This is funny. That James Webb image was supposed to be on the list. Still learning how to use this program. But yeah. So is it Cygnus X1, M87, or Sagittarius A? Nice work. All right, let's take a look at our leaderboard. See who gets the bragging rights.
The winner is...
Leaderboard, the winner is SB.
SB.
Nice work. So you're the fastest. Almost 4,000 points. Very nice. Very nice.
Fastest.
All right. So now we're pretty much at the end of our time. I do have a couple more questions I'd like to ask you. Just first of all, did you have fun? And yes, we got... Yay. We still only have 2 people on, but this is a good percentage. We're happy. And now these are for our under 18 audience. We hope there's some of you out there under 18. And we want to know, did you learn anything about Canada's activities in space? Like maybe that we're awesome at astrophysics and we have time on the James Webb Telescope.
No.
And we have a cool observatory at York University. We only have,
Okay.
no. Oh, you know what? That's my son, Emmerich. He's always like, no, I already knew it all because my mom's in space.
Can't teach
That's
him anything.
okay. That's good. Okay, we got 2 people on. And then Em's going to say no to this too because he's already totally wants to be an astronaut. He's interested in space and STEM, but yes.
He's like, how could I be more interested in it? I'm already at my max level of interest.
Yeah, I can't get any more interested. I'm all in already. That's my son. Yeah, it's awesome. All right. So that brings us to the end of our program. Are there any last things you'd like to share, Jesse? Any last comments or?
I guess the only thing I want to add is like one of the best things about astronomy is going out and looking at it yourself. So it's such a great thing to do with friends and family. You can, take some precautions, like make sure you wear the right clothing, make sure people know where you're going, make sure you bring food and water and a charged cell phone, but go somewhere at night, plan it out, find a good place to go, bring a chair and look at the night sky because, we can talk about it on the computer and you can look at cool pictures and you can really geek out on it. And I'm going to do that for the rest of my life, but it doesn't substitute for getting out and going to see it. And Canada has some great skies to see from. So try and do that. It's a lot of fun.
Oh, and this is great. Matt Graveline's letting us know that he accidentally said no.
Yes. Okay.
I'll fix the data. That'll be good. All right. Well, thank you so much for joining us. To those of you who did join live, if you like this, consider donating through Eventbrite or just like and subscribe for more of this content. I am sad to say that we have a hail and tornado warning in Sudbury, so we will not be meeting in person to get out there and look at the stars in real life. But as Jesse said, get out there as much as you can. It's just, yeah. I'm also happy to announce that the Canadian Space Agency has sponsored our star parties, virtual and in person. Yes, yay. So we're going to keep them going. For October, we are going to join the Halloween festivities at Dynamic Earth on Fridays. So if it's clear, we'll be there with the telescope. You can come take a look at it, see the moons and all of that of like the Galilean moons and the moon. And yes, good times. And we're going to take a little break. Our next virtual star party is going to be in November. So stay tuned for that. And thank you. Merci. Miigwech. Keep looking up.